Supply chain attacks, from Orion to AI agents. How does a trusted software update become a backdoor, and what's next? MITRE attack T195.2. Before SolarWinds, many organizations operated on an implicit trust model. You downloaded an update, verified the signature, and deployed it. The assumption was that if the vendor signed it, the code was legitimate. This diagram illustrates that traditional flow. The developer commits code, the build server compiles, signs, and the update server distributes. The customer downloads, verifies, and installs. The fundamental problem here is the single point of failure within the vendor's build and distribution pipeline. The SolarWinds attack, specifically the Sunburst backdoor, exploited this trust. Attackers gained access to SolarWinds' build environment. They inserted malicious code into the solarwinds.orion.core businesslayer.dll component. This wasn't a separate malicious file. It was part of the legitimate compiled binary, signed by SolarWinds. The callout here shows that the build server itself was compromised, allowing the malicious code to be injected before signing, making it appear legitimate. This specific binary, when loaded by the Orion service, initiated the backdoor. A critical factor in the SolarWinds incident was the privilege level of the Orion platform. The SolarWinds Orion service typically runs as system or a highly privileged domain account. This meant the injected Sunburst backdoor inherited these privileges directly upon execution. This wasn't a privilege escalation step. The malicious code started with maximum permissions on the host. This allowed it immediate access to sensitive system resources, local credentials, and network communication capabilities without needing further exploitation. This is why compromising Orion was so high value. Once the solarwinds.orion.core.businesslayer.dll was loaded by the Orion service, the Sunburst backdoor would execute. It performed several checks before activating, including ensuring it wasn't running in a sandbox environment and waiting for a specific delay. The code snippet here shows the initial hook point. Notice the use of legitimate SolarWinds methods, making it harder to detect behavioral anomalies. The initialize method, a standard part of the component lifecycle, was leveraged to kick off the malicious logic. The Orion Improvement Business Layer class was specifically targeted. A key technical aspect of Sunburst was its C2 communication, which initially relied on DNS and HTTP. The malware would construct a unique subdomain using a domain generation algorithm or DGA incorporating system identifiers. This DGA produced a seemingly legitimate domain, often ending in vsvmcloud.com. It would then perform DNS queries for this domain. If the DNS response contained a CNAME record pointing to a specific IP address or another domain, that served as the actual C2 server. This technique blended C2 traffic with regular DNS queries, making it harder to spot without deep DNS inspection. MITRE T1071.01. Sunburst wasn't a single monolithic payload. It operated in stages. First, the solarwinds.orion.core businesslayer.dll executed its initial checks and established initial C2. Second, it would receive commands including instructions to download and execute additional modules such as Teardrop or Rainbow Drop. These second-stage payloads were often loaded directly into memory using reflective loading, avoiding disk presence. This multi-stage approach allowed the attackers to maintain a small initial footprint and only deploy more invasive tooling on high-value targets. This made detection significantly more challenging, as only the initial C2 traffic might be visible. Once the Sunburst C2 delivered the second stage payload, typically Teardrop or Rainbow Drop, it was loaded directly into memory. This is a common technique to avoid leaving artifacts on disk. Teardrop was a custom Cobalt Strike loader. It would inject itself into a legitimate process, often svchost.exe, and then load the main Cobalt Strike beacon payload. This made attribution and forensic analysis harder, as the malicious code resided only in volatile memory. Detection often relied on identifying the beacon's network traffic patterns or memory-based anomalies, rather than file hashes. This command is a simplified representation of a memory injection, targeting a process ID. With the Cobalt Strike beacon active and running with system privileges, the attackers moved to credential theft. A primary target was LSAS.exe, the local security authority subsystem service, which stores credentials in memory. They would dump LSAS.exe memory to extract plaintext passwords, NTLM hashes, and Kerberos tickets. Tools like Mimikatz are commonly used for this, though the attackers often used custom or modified versions to evade detection. This step is critical for moving beyond the initial compromised host and gaining access to other systems in the domain. Mitered 3-byte arrow 1. Armed with stolen credentials and a map of the network, attackers performed lateral movement. Common techniques included pexec or WMI, Windows Management Instrumentation, to execute code remotely on other machines. They also exploited valid accounts to access administrative shares, SMB, or establish RDP sessions. The goal was to reach domain controllers, critical servers, or data repositories. This diagram shows a typical flow, from the initially compromised Orion server to a domain controller, often using stolen administrator credentials obtained from lsas.exe on an interim host. MITRE T21002, T21006. The SolarWinds attack focused on a trusted commercial software vendor's build pipeline. However, the attack surface has significantly expanded. Today, open-source software dependencies are a major vector. Instead of compromising a single vendor, attackers target widely used libraries or packages on public repositories like NPM or PyPI. The table here highlights the shift. In the SolarWinds model, attackers had to insert specific malicious code into a specific product. With open source, they can inject malicious packages that developers unknowingly pull into thousands of applications. This can be through typo squatting, where a malicious package mimics a popular one, or dependency confusion, where internal package names are exploited. Looking forward to 2026, the AI agent supply chain introduces new complexities. AI agents often integrate with multiple plugins, retrieve data from various external sources, and even use other AI models. Each of these components represents a potential supply chain vector. A malicious plugin could be injected, a poisoned model could be deployed, or even prompt injection attacks could manipulate the agent's behavior. This diagram shows how an AI agent relies on various external components, each a potential point of compromise. For example, a malicious data retrieval plugin could exfiltrate sensitive data or, while not a direct build system compromise like SolarWinds, preventing supply chain attacks starts with securing the build pipeline itself. This means applying zero-trust principles to your CI/CD systems. First, isolate build agents. They should be ephemeral and have network access only to necessary resources. Second, implement strict access controls on source code repositories and build artifact storage. Third, enforce code signing best practices, ensuring keys are securely managed and signing processes are automated and tamper-proof. Lastly, integrate static application security testing, or SAST, and software composition analysis, SCA, directly into the pipeline to catch vulnerabilities and malicious code early. A common mistake is allowing build agents broad network access or using long-lived credentials. Even if a compromise occurs, you need to limit its blast radius. Microsegmentation is key. Isolate critical applications and services into their own network segments. For example, your SolarWinds Orion server should not be able to initiate outbound connections to arbitrary external IP addresses or communicate freely with your domain controllers unless explicitly permitted. Egress filtering is crucial. This example shows a firewall rule, simplified for illustration, that would block suspicious outbound DNS queries or C2 beaconing to unknown destinations. The rule specifically allows known good DNS resolvers and then denies all other outbound DNS traffic from the Orion segment. This would have helped detect Sunburst's DGA-C2. Finally, you need visibility into what's running and what it's doing. Maintain a software bill of materials, or SBOM, for all applications, detailing every component and its version. Tools can generate these automatically. At runtime, monitor process behavior. This KQL query, for example, looks for suspicious lsas.exe process access, a key indicator of credential dumping attempts like those used by Teardrop. It identifies when non-standard processes attempt to access as.exe memory. This kind of detection rule, combined with EDR telemetry, is crucial for catching post-exploitation activity, even from signed binaries. Common mistake: not having clear baselines for expected process behavior. Supply chain security requires securing the build pipeline, micro-segmenting runtime environments, and continuously monitoring for behavioral anomalies from trusted binaries, even more so with the rise of AI agents. Subscribe for weekly technical deep dives from ViewNet.